Hello everybody, welcome back to All Things Nautical. In today's video we're going to have a look at Composite Great Circle sailing. So the first question you may have is, what is a Composite Great Circle sailing? So basically it's a sailing route followed by a ship, but instead of following a standard Great Circle route like you can see over here, we're going from A to B. We would follow a great circle along this yellow line, and this track would carry on arcing downwards until it basically reaches the vertex. It's more or less about there somewhere, and then curve back upwards towards B. So we're following a great circle, so this would be an arc or a segment of the great circle going from A to B. Now a composite great circle is basically a track that's been limited or restrained to a specific latitude. So the company, for instance, could issue a warning, or you could receive a navigational warning. Let's say you've got, in higher latitudes, you've got a warning, for instance, for ice. Somewhere down here, there could be a warning for floating ice, and your vessel's trying to avoid that. So that means you're going to try and not go past or higher than a certain latitude. So this could also be imposed by the company, of course, being a navigational restraint, saying that when you're proceeding on your track from A to B, you're not allowed to go higher than a specified latitude. So in that case, we'd be heading down this track, going eastwards in the southern hemisphere, heading southeast, getting to a point V. Now, at this stage we get to V, this latitude over here would now be that imposed maximum or restraining latitude. So let's say this is 50 degrees south, just to use an example. So you'd be sailing along your great circle until you get to a point of 50 degrees south. When you get to 50 degrees south, you can't really go any further south because you're now restrained to this maximum latitude. So that means we're going to follow this parallel of latitude at 50 degrees south. Going eastwards, we're going to stick on this parallel of latitude. We're going to do parallel sailing, follow the parallel of latitude all the way through up to V2. And at V2, we're getting to a point where we would now cross back onto our original great circle track heading up to B. So we go by great circle down to V, V1. Then we switch over to parallel sailing. We sail along our parallel of limiting latitude at 50 degrees south up to V2, and then turn back onto our great circle, finishing our course, our track back up towards our destination at B. So instead of having one continuous track segment like we would in standard great circle sailing, we now have three. So we have a great circle track, a parallel sailing Rhumb line track, and then another great circle track. So we're actually doing three tracks in one route. So that also means we're working in three triangles. So we've got a triangle to the left here with PV1 and A, and we've got a triangle on the far right with PV2 and B, and we've also got a triangle PV1 and V2. So that means we can use then Napier's rules to solve most of these calculations regarding composite great circles. So in today's example, we have a track having a limited latitude again in the southern hemisphere at 56 degrees 10 minutes south. We're going from Cook Strait, New Zealand in the eastern hemisphere to Cape Horn, which is in the western hemisphere. So the first thing that we note here is that we're staying in the southern hemisphere. Okay, so from 41 south to 56 south, and we're going from the eastern hemisphere to the western hemisphere. So that means we're sailing eastwards, firstly, and secondly that we're remaining in that southern hemisphere. Now, the next thing that's interesting here is that this limiting latitude, so we've got a limiting latitude of 56 degrees 10 minutes south, and that latitude is the same, it's numerically equal to the latitude at B. So if we're looking at a diagram then for today's example, we're going from A eastwards in the southern hemisphere, so we're going southeast towards the limiting latitude at V1. Then, of course, we're going to do parallel sailing. So we're going to go 90 degrees along that parallel of latitude to get to B. So because V1, or the limiting latitude, and the latitude for B is numerically equal, we're not going to curve back onto a great circle track like we would have in another example, or in the one that I showed you earlier. So in this case, we're only working with the two triangles. So we've got a triangle to the left here, which has our great circle segment. And then we've got a triangle to the right that has our parallel sailing segment. So in order to get, for instance, the distance from A to B, so we're going to calculate a distance along this track. We're going to be calculating two segments. We're going to do a great circle, and then we're going to do a parallel sailing calculation. So the question says we're going from New Zealand to Cape Horn. The ship reports a departure position at 14:15, so that means we're going to have to calculate an ETA at Cape Horn, just doing 20 knots, it's 2012, and then we're also given the standard time zones, which we will then use in our ETA calculation. So the first thing that we can do is we can have a look at some of the info that's already given. So just like in a normal great circle, we had a couple of pieces of this triangle that we can find values in the triangle, rather, that we can find just from the question. So the question gave us the latitude of A, and if we know the latitude of A, that means we subtract that latitude from 90, and we're going to get this side of this triangle here, PA, because the two are complementary. Likewise with PB, we know the latitude for B, that means we can find PB, 90 minus latitude B, and the same also for the maximum latitude. So in this case, we don't need to calculate the vertex, the latitude for the vertex. We're actually given the latitude for V. So that means that if we take that latitude subtracted from 90, we're also going to get PV. Now, with regards to angle P at the bottom, the polar angle, we don't know angle P1 and P2, so that we'll need to calculate. So part of these questions, typically, when you encounter a question like this, you'll be asked for the distance that's being sailed along the track, the initial course that you're going to steer when you start. If we had a further segment up here past V, you would have also been asked for the final course, and then of course you'd be asked for the coordinates of the actual waypoint. Now the latitude is known, that's quite straightforward, but then the longitude we will need to calculate, and we're going to do this in today's example. So this triangle on the left, we can use Napier's rules. Now, we're looking at the triangle, so we know PA is given, or we can calculate it, and PV we can calculate also quite easily. So that means if we know PA and PV, we should be able to solve any other section in this triangle. So we can use that to calculate the distance AV, and we can also use it to calculate angle A, and we can also use it to calculate angle P. So everything that we need to know with regards to the question, we'll be able to find through Napier's rules. So first things first, have a look at all of these values and save them up, store them in the calculator. So the first one is the d longitude from A to B, so that's the total d longitude from A to B, and that's going to be 118.3 degrees east. Then we also have side PA, which is 90 degrees minus latitude A, side PB, which is 90 degrees minus latitude B, and of course side PV, which should be numerically equal to PB in this case, and that of course will be 90 degrees minus latitude V. So all of these values we will then use to start off our calculation. So the first thing that we're going to calculate here is going to be distance. Now if you look at this formula, so in Napier's rules, we could have said that cos PA would be sine of it, or cos of its opposite. So the rule says sine middle part is equal to cos opposites. So this PA, because it's below in the bottom half of the circle, will be complementary, so that becomes cosine PA is equal to cos AV times cos PV. That's our formula that you can see over there. Now if you rework that to make AV the subject of the formula, it looks like this. So cos becomes cos PA over cos PV. and that of course we can then calculate, and that's going to give us 0.79376. We get the arc cosine or the shift cosine of that, and that's going to give us this value over here. So this angle AV, and of course we know that because it's part of a great circle, all sides of great circles are measured in degrees, minutes and seconds. So we can get that measurement then, which is going to be an arc. So that's a great circle arc or a segment arc. And because it's a great circle, 1 minute along a great circle is equal to 1 nautical mile. So that means we can take this value in degrees, we multiply it by 60, and that's then going to give us the distance of 2,247.7 miles. So that'll be the distance from A to V. So that's the distance for the beginning of our track, from position A going down towards V1, where we start on that maximum latitude. So the next thing that we need to calculate then is going to be the longitude for position V. So if we're going back up to the top here, we see that in the question at the beginning we've actually given the latitude for V. So we know that the latitude for V is 56 degrees 10 minutes south. So we know the latitude, we don't know the longitude. So if we want to know where this vertex is, where is vertex 1, the location of vertex 1, we've got a latitude given. Now we can calculate the longitude by calculating angle P1. So that's our next step. We're going to be calculating angle P1. And if we look at our diagram, this angle P1 is going to be the difference in longitude, because remember the longitude or difference in longitude is a polar angle. It's always a polar angle, so it's got to be measured down at the pole. There's a polar angle, which is the measurement, the difference in longitude from A to V1. So this angle P1 is going to be the D long there that we want. So this is given latitude, and now we're going to calculate P1. Now in order to calculate P1, we now know AV. We just calculated AV. So AV is known, PV is known, and PA is known. So there's two options you can follow here. By Napier's rules, you can either say that cosine angle P, which of course will become sine angle P because it's below at the bottom half of the circle. So it becomes sine P will be equal to tan PV over tan PA. So that's one route that you can follow. Or you could have also made PV the center part and say cosine of PV will be equal to tan AV over tan P. And then rework that formula to make P the subject of the formula. So in my calculation here, I've done just that. I've made P the subject of the formula using AV and PV, and tan P1 then becomes, or tan P1 will be equal to tan AV over sine PV, and that is equal to 1.37. So that means that the angle P1, so we get arctan of that, the angle P1 is equal to 53 degrees, 53.99728 degrees. And this of course will be east of A, because we're going eastward, so it must be east of A. So that means that to find this position V1, okay, so the latitude and longitude for V1, we've now calculated, we can now calculate this altogether. So the latitude, which was given in the question, is 56 degrees 10 minutes south, and now the longitude we know is 53 degrees 9.99728 east of A. So the longitude for A is 174.30 east, and we're going further east. So all we got to do is we take the 174.30 east, we add 53.99728 degrees, and that's going to give you an angle of 228 and a half. Now we know that the longitude can't be 228 because longitude is a minor polar angle and it can't exceed 180 degrees. So that means that this angle of 228 and a half will need to be subtracted from 360 to get the minor polar angle. So the 228 and a half is a major angle. Subtracted from 360 will give us a minor polar angle, and as soon as we subtract from 360, that means we are changing direction. So 200 degrees east would be 160 degrees west, for instance. So this 228.5 we subtract from 360, and that's going to give us a value of 131.5. So 131 degrees 30.2 minutes west. Now, because we subtracted, so we changed the direction, so instead of east it becomes west, and this now gives us the longitude for V1. So now we have V1 calculated, fully calculated. So we have the latitude of 56 degrees 10.6 minutes south, and 131 degrees 30.2 minutes west. So that solves the position for V1. The next thing that we need to do, there's two things remaining. One is to find the distance from V1 to B so that we can find our total distance. And then we also got to calculate the angle, the initial angle that we set sail on to get from A to V1. So the initial course on the Great Circle. So if we're looking at our diagram here, so we're going to calculate angle A, get from A down to V1. So we're going to calculate angle A, that's going to give us our initial course. And then we still need to calculate this distance here. So to find angle A, we're going to use Napier's rules. We're going to go back to the cartwheel. Now in this case, all of these values are known. So you can pretty much use any formula you like. So we've just calculated angle P1, so we can use that. And then we can use PV, which was given. So in this case, we're going to have angle A, so sine middle part equals cosine opposite. Now this becomes a cosine, so cosine A is equal to cosine PV multiplied by sine of angle P1. And that's going to give us angle A. So you can see cos PV times sine P1, that gives us a value of 0.672. Now we get an arc cosine of that, and that's going to give us an initial course angle. Now the initial course angle we know is southeast because we're in the southern hemisphere going eastwards, so that means our initial course angle will be southeast. 47.7 degrees or 0.8 degrees around it. Now we're going south and east, that means we are going to subtract this angle from 180, so 180 degrees minus our course angle, and that's then going to give us an actual course of 132 degrees true. So departing A, we will depart at a course of 132 degrees true to set forth on our Great Circle. So that now solves the initial course as well, which means the only thing that's left is this run track distance over here, VB, and then we can of course add those two distances together, and that's going to give us our final distance, which we can then use to calculate the ETA. So in order to find this distance for VB, if we're doing parallel sailing, it's necessary for us to know what the longitude is. So we need to work with the D longitude, isn't it? Because in parallel sailing, because we are following a parallel of latitude, we know that the distance along the track is equal to the departure, the eastward movement of the ship, east or westward movements of the ship. So because distance is equal to departure, all we need to do now is calculate the departure, and that will give us our distance. Now, for departure, to calculate departure, we need the longitude, because departure is equal to d longitude in minutes multiplied by the cosine of the mean latitude, as you can see in this formula over here. So we need the d long for VB, so that's going to be angle P2, which of course will multiply by 60 to turn degrees into minutes, and we got that value in minutes, and that we will multiply then by the cosine of the mean latitude. But in this case, we're looking at our example here, we don't have a mean latitude, we're only following a single latitude, isn't it? Which means that this max latitude is the latitude that we're working with, so that's going to be the latitude that we are also placing into the formula. So we're going to find P2 first. That's what we need first. We need to find this d longitude P2. Now we've just calculated P1, and we already know what the d longitude from A to B is, because that we got from the question right at the beginning. So we're going to take that maximum d longitude, we'll subtract P1, and that's going to give us angle P2. So we'll do just that. So for angle P2, we're going to take 118.3 degrees, we're going to subtract 53.99, and that's going to give us 64.3 degrees, and that of course will be east of V because we're still traveling eastwards. Now this value of 64.3 is a value in degrees, so it's a d longitude in degrees, which means we will multiply it by 60. So in this formula, so in order to calculate this distance, we're going to take this d longitude, which is this value, so you can recall this value, multiply it by 60, and then we're going to use the latitude for our vertex, which is our maximum latitude, our limiting latitude, which is 56 degrees 10 minutes, cosine of that value, and we're going to take this longitude in minutes multiplied by the cosine of that maximum latitude, and that's going to give us then a departure. And because we're doing parallel sailing, we know that departure is equal to distance, so that means that this value is also equal to our distance, and that's going to be 2149.26 miles. So that gives us that distance there. So now we have both distances. We know the distance AV, we've calculated that, and we've now also calculated distance V1 to B. So we add those two together, that's going to give us our total distance on the track. So 2247.7 plus 2149.26. We add the two together, and that's going to give us a total distance then of 4,396.96. So we've now solved everything that we needed except for the ETA. So we've got everything with regards to the track and the courses has been solved. So we've now got a total distance, we have an initial course, and we've calculated the position of V1. So the only thing that remains is the ETA. So we were given a departure time of 14:15 New Zealand Standard on the 3rd of August 2012, and the vessel is steaming at 20 knots. So there's no change in speed, there's no stoppages at any ports, it's just one continuous route. And we've also been given the time zone, so New Zealand Standard Time, which is 12 hours ahead of Greenwich, because it's in the Eastern Hemisphere. And then of course we're going to Cape Horn, which is near Chile. So then we'll keep Chilean Standard Time, which is in the Western Hemisphere, of course, which means it's 4 hours behind Greenwich. So the best way to do this, just as we do with any other ETA, is we're going to convert everything to GMT. And the reason why we convert to GMT is because we're then eliminating the whole process of having to subtract or add days when we cross the date line. So if you can see from this example, of course, when we go from east to west, that means we would have then repeated a day going from the eastern to the western hemisphere. So to avoid that adding or subtracting days, we just go back to GMT because that just makes it a lot simpler. So we're in the 3rd of August at 14:15 New Zealand Standard Time, and the first thing that we're going to do is we're going to apply the standard time difference for New Zealand. This should be NZ, not F. So New Zealand Standard Time, which is 12 hours ahead of Greenwich. So to get back to Greenwich, that means we're going to subtract the 12 hours. So we subtract the 12 hours, and we're still on the 3rd of August at 02:15 GMT. So 2:15 in the morning GMT. Then we're going to apply our change in time. Now the change in time we're going to calculate by using the total distance divided by speed. So our total distance of 4,396.96 miles divided by 20 knots, because the vessel is doing 20 knots, and that's going to give us a change in time in hours. Now this value that you get will be a value in hours, and that of course we need to convert into days, hours, and minutes. So this value is going to give you a value in hours, which you will then divide by 24. When you divide it by 24, you're going to get 9. So you're going to have 9 days, 9.16. If you have 9 days, and you subtract the 9, you're going to be left with that remainder of 0.16. Multiply that by 24 again, and you're going to get back to a degree, or back to a value in hours. Now that value in hours will then convert to hours, minutes, and seconds, you're going to have 3 hours, 50 minutes, and 53 seconds. So this is our change in time. So doing this distance of 4396.96 at 20 knots, it's going to take us 9 days, 3 hours, 50 minutes, 53 seconds to complete this trip. So we will then, of course, add this change in time to our departure time, and that's going to give us to a new date of the 12th of August. So add 9 days, it's the 12th of August, and we add the time there, and we're going to get 6 hours and 6 minutes. We can just round it to the nearest minute. We're not worried too much about the seconds. And when you're giving this as an ETA, you're probably going to give it at 6 o'clock. You won't really give it at 6:06. So it's going to give us 6:06, and that, of course, will still be GMT. And the last thing then what we need to do is we need to convert this to Chilean time, to Chilean Standard Time. Chilean Standard Time will be west of Greenwich, so it's behind Greenwich. So again, we will be subtracting. So we've got a 4-hour change there. So we're going back 4 hours from Greenwich back westwards. As soon as you travel westwards, you must subtract. So we're going westwards by 4 hours. So we subtract 4 hours, and that's going to give us 2 o'clock in the morning, 6 minutes past 2 in the morning, Chilean Standard Time. So that is an example of a composite great circle sailing question where we solved the distances for both the separate components of the track and also the final distance. We found a final true course. We had a look at calculating the position of V1 on the track, where we're actually switching over from great circle to Rhumb track, and then we calculated at the end an ETA. So thank you guys for watching, and I'll be uploading some more great circle videos within the following couple of days.